Thank you very much. First, we'd like to thank the PP7 organizers for the excellent conference. And also thank you very much for the opportunity for us to give a talk about our book chapter, which focuses on geophysical evolution during rocky planet formation. And the chapter authors include Tim Lichtenberg, Laura Schaefer, Miki Nakajima, and Rebecca Fischer. So today, Tim and myself are giving a talk on this book chapter. So here is a list of rocky planets in a solar system. And as you can see, the planetary system is very diverse. The Earth is the only known habitable planet, which has a surface ocean, plate tectonics, and have life on the surface. And Venus is very close to Earth in many ways, but it's very different. It doesn't have life on the surface, and the surface temperature is very high. And Venus is very different from the Earth. And Mercury is known to have a huge iron core, and Mars may have had a liquid ocean, but not anymore. So the planetary system is very diverse. And of course, building blocks of these planets are very important. But in this book chapter, we like to stress the importance of geophysical processes. So geophysical processes played an essential role to create diversity of rocky planets. So here is the quick summary of our book chapter. So we start with the planetesimal stage, where the planetesimal could experience extensive melting, and that leads to extensive degassing and also interior evolution. And then we follow the protoplanetary evolution and reach the protoplanet stage. And once that happens, the protoplanet experiences giant impacts, experience extensive melting, and also differentiation. And over time, magma ocean crystallizes. The magma ocean reacts with the atmosphere that determines the initial composition of the atmosphere. And over time, magma ocean crystallizes and experiences solid state convection and also have some delivery from meteorites. Then this brings us to us today. So today, we're going to discuss each step of rocky planet formation. So here, we like to start with a discussion of two reservoirs in the inner solar system. So these are two meteorite types. One is a chondrite and a chondrite. So this morning, Steve already gave an excellent talk about these chondrites. And the chondrites are undifferentiated meteorites. As you can see, this includes chondrules and CAIs, so they never experienced melting. In contrast, chondrite experience melting, also differentiated. And this chondrite can be categorized into two distinctive groups based on their isotopes. So this reflects the nucleosynthetic isotopic effects. So one is the carbonaceous chondrite, CC, and the other one is the non-carbonaceous chondrite population, NC population. So this can be clearly seen on the figure on the right. This is shown in the isotopic phase space in the chromium and titanium. And the blue indicates CC population, and the red indicates NC population. So clearly, you can see that there are two distinctive isotopic groups. And the green shows Earth, Moon, and Mars. Now we are looking at two distinctive populations as a function of time. Here, x-axis is a time after CAI formation. And as you can see here, the red still indicates NC population formed early, compared to a CC population that formed later. So you can see that there's a time offset between NC and CC populations. And NC is indicating planetesimals formed in the inner solar system early, and the CC is indicating population of the planetesimals formed later in the outer solar system. And this line shows the BSE. BSE is the bioxylic Earth composition. And as you can see, BSE is a mixture of NC and CC populations. So what's the origin of NC-CC dichotomy? So this is a very great question and a big question in planetary science. And there are several hypotheses, so we are introducing two hypotheses. The one on the right is due to the presence of Jupiter. So the red circles indicate NC population, which is the planetesimals from the inner solar system, and the blue indicates CC population that forms in the outer solar system. So the top panel indicates the weather classical co-formation model, and the bottom one indicates a February accretion scenario. And in both scenarios, the presence of Jupiter prevented extensive radio mixing between NC and CC populations. The figure on the right shows another hypothesis. So according to this hypothesis, the movement of isoline created two distinctive populations. So that could explain the NC-CC dichotomy. Again, origin of the NC-CC dichotomy is a very important question and a very key question to be addressed. So now we talked about the source of materials. Let's move on to the planetesimal stage. So as we talked from Mikael's talk, the streaming instability creates 100 to 250 kilometer size planetesimals. The figure shows the particle density as a function of time. And you can see that the formation planetesimals in the last panel, the circle indicates the Hill radius. And these planetesimals are relatively cold because these planetesimals are relatively small and didn't experience extensive heating event due to the accretion event itself. However, they could experience extensive heating due to the radiogenic heating of aluminum-26, as we heard in Steve's talk this morning. So what's the effect of the heating? So this figure shows the maximum planetesimal temperature as a function of planetesimal formation after CAI, and also planetesimal radius. So as we heard earlier today, the half-life of aluminum-26 is very short. So if a planetesimal formed early, then the extensive heating from aluminum-26 is important. But if they form later, the heating effect from aluminum-26 is negligible. And so the heating has a huge effect on the interior conditions and also volatiles in the planetesimals. The figure on the top shows the evolution of volatiles. Once planetesimals experience extensive heating event, volatiles could escape from the planetesimal. And such effects has been actually seen in meteorite. In the Newcomb et al. Paper, which published very recently, looked at the achondrite and then find that the volatiles escape from the achondrite, so which is consistent with the picture shown here. Also, the extensive heating can also lead to a differentiation within planetesimals. And also, the extensive heating can turn silicate solid rock to magma motion. So the importance of, here we hope that we convince you that the importance of tracking the evolution of planetesimal interiors. So we talked about planetesimal stage, so let's move on to the protoplanet stage. So during the protoplanet stage, as we heard earlier today, the protoplanets grow by pebble accretion as well as mutual collisions. And then once protoplanets reaches larger than 1,000 kilometers, they could experience extensive heating and also melting. So here is a list of energy sources for rocky planets. And the top one is the gravitational energy due to accretion. The second one is the energy due to differentiation, impact, and radiogenic heating, and also phase transitions. So when we are considering large rocky planets, the gravitational energy due to accretion becomes significant. When we are considering Mars-sized or Earth-sized objects, the gravitational energy itself can create the temperature of thousands of kelvins. So this is very significant. And as a result, these protoplanets can experience extensive melting, and as a result, differentiation. So during the process, chemistry of a planetary interior also change over time. So this is a schematic view. The impactor hits a solid mantle of a growing planet, and the impactor's core becomes small fragments and turbulent mixed within the magma motion, which is created by the impact event itself. And the iron, the impactor, and the silicate experience so-called metal-silicate equilibration. So some elements love to stay in silicate, so they move to the silicate phase. So these elements are called lithophile, or rock-loving elements. And some elements love to stay in iron, so these are called the siderophile elements. And so these elements are exchanged at the interface, and eventually the iron is delivered to the core of the target. And as a result, the core becomes rich in the siderophile elements, and the silicate mantle becomes enriched in lithophile elements. This is how the planetary chemical evolution works in a protoplanetary stage. But I also want to stress the importance of understanding the efficiency of metal-silicate equilibration. So this is also a big unknown. There are two approaches shown on this slide. So one approach is looking at impact event using numerical simulations. And so here is the target, here is the impactor. So during the impact event, you can see part of the impacted core falls onto the target's core. So there is a direct merger. But also there is some mixing between the core of the impactor and also the target. However, it is well known that in these simulations, mixing between the core of the impactor and the mantle are underestimated due to numerical resolution. So another approach is shown here in experiments. So here is the experiment of the impact. So this is the liquid blob, which represents the impactor, and this represents a target. So both of them are fluid. And the impactor hits the surface of the target, that creates a crater, and eventually the impactor becomes small fragments and turbulent mixed over time. So as you can see in this scenario, the target is, the impactor core is more mixed with the target mantle, because experiments can reach much higher resolution. And the previous studies indicate that impactors that are smaller than 100 kilometers in radius, its core could be fully equilibrated with the target mantle. But if impactor is much larger, the impactor may not have enough time for its core to be fully equilibrated with the mantle. So the efficiency of equilibration depends on the type of the impact. And also, the experiments can reach a much higher resolution than the simulation could, but also this is still not quite perfect. So it's very important for us to understand how efficient the metal-silicate equilibration is to understand the chemical evolution of planets. And so far, we talked about very classical view, which is shown in B. But also, here we are showing various modes of core formation scenarios. In A, we are considering pebble accretion scenario. If there was a pre-existing shallow magma ocean, and if the pebble accretion didn't provide enough heat, then pebble may just experience metal-silicate equilibration at the relatively shallow magma ocean. And if the impact was much larger, then it's possible that the part of the core didn't experience metal-silicate equilibration and just directly merge with the target's core. And if the impact is so energetic, then it could completely melt the mantle, and also the mantle silicate, and also iron becomes completely miscible. So they become completely mixed. And the metal-silicate equilibration can happen only after the magma ocean experiences some extent of cooling. So this could provide a very different picture of metal-silicate equilibration. So here we like to introduce a key concept, which is oxygen efficacy. Here, this is a chemical potential of oxygen, and which is expressed as following. R is a gas constant, and T is a temperature. And FO2 is the oxygen efficacy. And oxygen efficacy is typically expressed as the relative to a reference. Here we are looking at the iron oosteite reaction. Here Fe reacts with oxygen and becomes FeO. And the reaction is shown as the following. And the log of the oxygen efficacy is expressed as the following. And here A is activity, and which is approximately written as the following. Here X is the mole fraction of FeO in a silicate, and the X, this is the representing a mole fraction iron in a metal phase. So this is experimental observable value. And so we talked about the iron-Unstite buffer, as you can see here. So the figure shows the different reference reactions. And y-axis shows the viscosity, and the x-axis shows the temperature. And there are different kinds of reference state we can refer to. And so this also depends on temperature. And the key concept here is that when FO2 is large, meaning that the system is oxidized, and if FO2 oxygen viscosity is low, which means the system is reduced. And according to previous studies, oxygen viscosity likely increased during planet formation accretion due to various processes we described here. So first, at high pressure temperature conditions, the Fe reacts with SiO2, and it becomes FeO. And also the Fe2 plus could become Fe3 plus iron under high pressures. So this figure indicates the iron disproportionation under high pressure. You see more Fe3 plus. And when we look at a large planet that has a large pressure range, so these planets may experience more iron disproportionation, and the mantle can get more oxidized compared to smaller planets. However, this reaction also depends on how efficiently iron is removed from the system. So that's something we need to consider. And also water delivery, subduction, hydrogen escape also affect the oxygen viscosity. And also in the recent paper, which was published yesterday, indicate the equilibrium reaction with the hydrogen, atmosphere, core, and mantle could also contribute to evolution of oxygen viscosity. Why do we care? Because it also affects the atmosphere. So this is a schematic view of atmospheric species as a function of oxygen, oxygen viscosity. So at the end of the planetary accretion phase, the Earth, the planetary surface would be covered by a magma ocean, and the magma ocean would be interacting with the atmosphere. And in a very reduced environment, the atmosphere will be enriched in reduced species such as CH4 and NH3. But here, looking at the more oxidized condition, the atmosphere will be enriched in CO2, H2O, and others. So the figure on the right also shows the same picture. When you are looking at reduced environment, you see H2, CO, and others. But in a more oxidized condition, you see more H2O, CO2 in these atmospheric species. And I also want to stress one point about the importance of a giant impact. So giant impact is thought to be responsible for forming our own moon. And the moon is very important for us, so it affects the length of the day and the ocean tides, and also potentially the stability of the obliquity. So that also affects the climate. And by understanding the planetary moon formation scenario, we can have a better understanding of the Earth and the moon system. And previous work indicates the relationship between the planetary and satellite masses. And if we are looking for Earth-like planets with Earth-like condition, it will be very important to understand the origin of the moon, and also the general understanding of the satellite formation scenario. So I will switch to Tim, the speaker.
All right, thank you so much, Miki. So far we covered the first half, essentially, of this diagram, going from the planetesimal stage, which is happening during the protoplanetary disk phase on timescales of 10 to the 6 years approximately, going to the giant impact phase. Talking here on timescales that are related to solar system accretion, we believe at least parts of this picture, of course, to be relevant for exoplanetary systems as well. But to stay a little bit in this picture at the moment that we derive from geophysical and geochemical constraints from the solar system, we have some really hard rock in your hand sample evidence on these timescales from the solar system that may also guide astronomical exploration of these processes in the diversity of planetary systems. So this is summarized with a variety of references here for which you please have a look into the chapter. On the right-hand side, for the terrestrial planetary bodies from the inner solar system that we have sample access to. So planets or moon-sized objects for which we can take samples and analyze them in the laboratory. And those this analysis is not just in the past 10 years, but it really improved substantially due to improved analytical and laboratory techniques, and yields a range of late-stage accretion timescales that are important to consider in an astrophysical context. What I want to particularly point your attention to, and I won't discuss every one of those timescales, are the timeframes for the Earth, for the proto-Earth and the end stage of planetary accretion. Specifically, those two blocks here indicate that the earliest time the core of the Earth, the metal core inside the Earth, finished forming was at 30 million years after the formation of the solar system, and potentially, specifically the crystallization of the magma ocean itself, went on to approximately 50 or 150 million years after CAI formation. This is substantially longer than the timescale of the protoplanetary disk and adds information that we need to consider for the timescale of the end phase of the accretion, the physical processes that go into this. What I find particularly fascinating here is actually this block, which indicates evidence for liquid water at the surface of the Earth right after the crystallization of the magma ocean and the formation of the first secondary atmosphere on Earth. That means immediately after the planet formed, it finally crystallized from its initially liquid state, it formed an ocean that has a number of substantial implications for the diversity of terrestrial planets in exoplanetary systems. Now, when these magma oceans operate, like Miki already introduced, the entirety of the planet is molten. And this stage is very poorly understood because we have very little evidence, actually, that we can analyze and understand these processes. The problem with this is that actually during liquid phases, the timescales of chemical equilibration, fluid dynamical instabilities are very, very short compared to geological and astronomical timescales. Everything happens extremely rapidly, on the orders of potentially hours, days, or weeks, but it sets the long-term evolution of the planet. To illustrate you how vigorously dynamic these systems are, this here is a fluid dynamical simulation of the terrestrial magma ocean. So this is the metal core at the bottom, the atmosphere at the top. The mantle is in the middle, and what you see is convection in the magma itself. Now this is for a Rayleigh number of 10 to the 12, and this is at minimum 16 orders of magnitudes below the actual Rayleigh number of the magma ocean of the Earth, and even lower, like the magma ocean Rayleigh numbers in super-Earth, for instance, will be much higher than that. Now, but even under these conditions, the entrapment of particles that can, for instance, be iron particles, silicate crystals, or even volatiles, is highly sensitive to the actual fluid dynamical conditions. And that means that many different things can happen on a qualitative stage that set the long-term structural evolution and chemical segregation of especially volatile elements during that phase. Now, we discuss in the chapter a number of things that are qualitatively concern this phase, and one of them is the mode of mantle crystallization. This one here on the left-hand side is the canonical view of how that's happened, bottom-up crystallization, where the first solids appear at the bottom of the magma ocean and the crystallization front moves upward. Why does it matter? Because in this stage, this is a pretty simple fashion. You can understand the relation of volatiles that are that are dissolved and partitioned in the magma ocean to that in the atmosphere via partition coefficients. In this case, which we believe now to be much more likely, a variety of inhomogeneous crystallization scenario, there's no direct relation anymore between the volatiles that are trapped in the magma and while the magma ocean is crystallizes and the ones in the atmosphere. For instance, if you crystallize from the middle out, volatiles, and for instance also iron, can be entrapped in the bottom part of the magma ocean and is essentially closed off from the evolution of the atmosphere at later stages. So that means we don't necessarily know which and how many of the volatiles stay in the deep interior of planets and which ones make it out. It is also related to planetary size. Small planets essentially experience typically inefficient degassing during the time scale, but very efficient core mantle segregation because the time scale of crystallization is rapid relative to the degassing time scale. Large planets, on the other hand, show very likely much stronger vigorous convection, and so volatiles degas efficiently, but cores may stay to some extent diffuse, which has substantial implications for the oxygen fugacity in the redox state that Miki introduced. Again, why should you care? Because the atmosphere atmospheric abundances of terrestrial planets strongly depend on the chemical segregation in the interior of planets. What is this? Again, in a very simplified fashion, very simplified manner of thinking about this, but I like this very strongly because it gives an intuitive understanding, is to think about the number of elements that are actually in the mantle of rocky planets during the stage after the crystallization of the magma ocean. So this here is a selection of the cosmochemically most abundant elements. And you see, they are plotted as a function of electronegativity versus atomic mass. So if your planet or your equilibrating chemical system is more on the left side here, then we talk about reducing systems. If it's more on the right-hand side, it's more oxidizing. Naturally, by gravity, these elements are separated from each other during planetary evolution because these elements at the top here are lighter and typically tend to escape to space, while those here at the bottom typically segregate to the core. And this leads to the Earth being a very oxidized planet ultimately, which degasses water and CO2 and SO2 by volcanoes, while potentially more reduced planets may actually experience degassing of H2 for extended time spans. This has substantial implications for exoplanets, for instance. What will we find? Now, in the Earth system, or in the solar system, our planets, the larger planets, typically are oxidized. This leads to a very important concept from atmospheric physics, potentially explaining divergence between Venus and the Earth. This important paper actually appeared 10 years ago when also in the same year when Protostars and Planet 6 was happening. And during the last 10 years, this community has sort of tried to understand the concepts and the underlying, the effects of this process here. So what is this? Let me explain it. What you see is the outcome of magma ocean crystallization simulations. You see orbital distance in astronomical units for a G-type star and an Earth-sized planets. This here is the final water inventory of the planet in Earth oceans, and the starting conditions differ in orbital distance and water mass fraction. So for instance, yellow dots have 10 Earth oceans worth of water, which is approximately the upper limit in the bulk silicate Earth. Now, planets on the right of a critical irradiation or orbital distance at a fixed time, they actually can cool down, retain their water fraction, and form oceans. Planets inside a critical irradiation, the runaway greenhouse limit, they don't. And they end up with much drier inventory because the heat that they can radiate away is much lower than the radiation they receive from their star. The only way these planets can cool is by photolysis and H escape. And so they only cool when they lost all their water. This is a very important concept. In principle, it is the foundation of the inner edge of the habitable zone, but it is reversed. This is a concept this here applies to immediately after formation of the planet and may influence the billion-year-long evolution of rocky planets. This is extremely important in the concept in the space of exoplanets because essentially nearly all exoplanets that we found so far in the density space of Earth-like planets orbit inside the runaway greenhouse threshold. This is shown here in this plot, showing planetary mass versus planetary radius. Each dot is an exoplanet with a measured mass and radius. The Earth is about here, and if you scale up the Earth, you follow this line. Now, what I want to point your attention to specifically is the color of the dots that cluster closely around the Earth-like line. They are all either magenta or red. That means, translated from day-side irradiation to a very conservative estimate of equilibrium temperature, all of these planets here, nearly all of those planets, are molten, either now or during very substantial episodes of their past, depending on the initial water content. Now, we've tried to synthesize our understanding from these concepts into a sort of phase space of atmospheric scenarios for rocky planets as a qualitative function of planetary mass and installation, where the climate regime that I just described, the steam and runaway greenhouse climates, are here dominated by steam and later on potentially abiotic oxygen. Separated by the runaway greenhouse limit from Earth-like planets that we believe are abiotically generally dominated by CO2, CO or N2. But the question here remains why the habitable zone in general is extended. Why is it so large? And this is related to what, as operating on the Earth, a planetary thermostat related to the carbonate-silicate cycle and ultimately plate tectonics and mobilite convection. So what is happening here is that CO2 is in the atmosphere, acts as a greenhouse gas, and if the temperature rises, the weathering reactions in the atmosphere via runoff and precipitation increase and store more carbon in the mantle, and the reverse. And this leads to a thermostat that regulates the CO2 content as a function of irradiation. So CO2 content in the atmosphere and irradiation are anti-correlated over cosmic time or geologic time. But we don't know if this regime operates in all planets, and very likely it does not. So this is a phase space of geodynamic regimes as a function of surface yield stress and eruption efficiency. So what is yield stress? Essentially, it is the amount of force you need to apply to a rock to break it. And it is essential to initiate subduction, and therefore lead to plate tectonics-like planet, like the Earth. Eruption efficiency is the amount of magma that is emplaced beneath the lithosphere or on top of it in volcanic eruptions. And so you see that the Earth-like geodynamic regime is here only at very low yield stresses. But other regimes are thinkable. For instance, most terrestrial bodies or planetary objects in the solar system exhibit a so-called stagnant lit regime, where the interaction of interior and atmospheric volatiles is strongly inhibited. There are many more different regimes that the geodynamic community keeps discovering theoretically and via inferences methods. For instance, episodic lit regime, which may have been very important in Venus' past or still be operating, but also terrestrial atmosphere-less exoplanets actually now open a new window, because we can, by using phase curves of exoplanets, we can potentially directly study the surfaces of these worlds without the atmosphere in the way. Now, this is actually it already, so I have enough time to properly summarize. So we started the talk by pointing out timescales of planetesimal formation, which are related to the processes that we have discussed during this week, which relates to the disk timescale and the redistribution of dust grains via pebbles. It shows the data from meteorites and forward modeling of the data points that we get from geochemical analysis points to the terrestrial planet formation, the inner solar system, starts extremely rapid, essentially together on the nearly contemporaneously with CAI formation, potentially during the class 1 stage already. But at the same time, analysis from the terrestrial planets indicates that the final phase of accretion is very protracted. So the terrestrial planets start the earliest to accrete, but they finish the latest. Now, all accretion scenarios that are suggested, either rapid pebble accretion or planetesimal accretion via essentially in the end phase due to giant impacts, suggest that rocky planets and exoplanets form in very hot magma ocean states. This means that accreted metals and volatiles chemically equilibrate between the core mantle and atmosphere of protoplanets, which is a very important concept here, because it means that the astrophysically accreted combination and fractionation of elements, specifically volatile elements, is reset during the geophysical evolution of rocky planets. And there's no direct relation between the atmosphere of a planet, and specifically rocky planets, and the accreted volatiles during accretion. But not all is lost, because we can use the hot exoplanets that we have current observational access to, that may not be so astrobiologically relevant at first place, it seems, but they will inform us in the next decade, until Protostars and Planets 8, about very crucial processes that tell us something not only of the evolution of our own world in the very beginning, that ultimately led to the environment that birthed the origins of life, but also on the potential diversity of habitable planets across exoplanetary systems. And that's it. Thank you so much for your attention, and we are happy to take any questions.
Okay, thank you, Miki and Tim. Time for questions from staff. Yeah, it was fast.
Peter Wojtke from Graz, Austria. My question is, you probably know the non-detection of TRAPPIST-1b atmosphere, so that is maybe closest to an ocean, a magma ocean planet, as at least we were hoping so, but it's not the case. So how do you, so would you say that these magma ocean planets always have to have atmospheres, or is that also possible more or less without atmosphere?
No, I mean, of course, the atmospheres escape. This is what is predicted in these phases. The amount of escape, of course, depends on a variety of things, and there are other much more in-depth reviews in these processes, so I don't think this stands in any contrast to what we've said here. I want to point out something specifically about TRAPPIST-1. So multiple people here have said that the TRAPPIST-1 planets are uniform in composition. If you look actually into it a little bit more in detail, they're not. There's a break in the equation of state that you need to be using between B, C, and the outermost planets, actually being evidence for the runaway greenhouse being effective in the system for B and C, but for the remaining ones not. So the non-detection of an atmosphere on TRAPPIST-1 just corroborates, at least in my view, at this point, the qualitative evidence that we have. We need to have much more detailed evidence. We need to do this for many more systems, of course, before we can draw actual conclusions about this process. But I don't think there's any anything against this.
I was just kind of commenting on your last point. You know, this is an opportunity, but what if they don't have atmospheres?
So some planets, ultra-short periods specifically, are so hot that they will be magma ocean planets that have magma oceans on their day sides, even if they have no greenhouse effect. Honestly, as a sort of hybrid geophysicist, this is the planets I'm mostly interested in at the moment, because we don't have the degeneracy from the potential atmospheric composition anymore. So, if this is the case, the universe operates, then so be it, and then we'll use the atmosphere-less planets to understand directly the geophysics and geochemistry of the surfaces and the convection timescales and redistribution of elements and refractory elements in these planets.
Okay, so you.
Jonathan Fortney, University of California, Santa Cruz. Really nice talk. I missed the driving point behind why the super Earths might not have a distinct core. I think you mentioned that convection might be very vigorous, but don't you still have an immiscibility and large density contrast? So I just wanted to come back to that.
Yeah, so this is it actually. So at very large Rayleigh numbers, the viscous stresses in the convecting system can overcome gravity and keep particles entrained exactly like you see it here. And at the moment, what we do to understand these systems is we use scaling experiments that are derived from ultimately buoyancy Rayleigh-Banach convection experiments in water tanks, because we cannot simulate these systems, as you see here clearly. And these scaling laws that are derived from those experiments indicate that above certain Rayleigh number that is relevant for super-Earths and sub-Neptune interiors, iron crystals for the Rayleigh numbers that are relevant for the magma ocean stage won't rain out. You know, this will happen inevitably, but in order to exchange the redox state of the interiors, you don't have to have no core. You only need to change the amount of iron that is stuck in the mantle by a minuscule amount. If you can do that, then you will change the redox state of the degas atmosphere. This is the point I try to make.
Okay. All right, thanks a lot.
Next, please. Front.
Hi, Diana Dragomir, University of New Mexico, USA, not Mexico. So my question is, how much do you know about, how much is known about whether volatiles, the volatiles trapped in a mantle, might be siderophiles or lithophiles? And could you use that information to figure out in that second crystallization scenario, which ones might get trapped below the solid middle layer and which ones not? Or does it not scale that way?
Short answer is we don't know. This is the future, I guess. Seriously, like, I think we need to do exactly this exercise, and I know from a few groups that have started to work in this direction. We need to very, very urgently understand, at least come up with some basic predictions that we can test observationally for this process here, because it's very likely to be very important for the solidus and liquidus behavior in super Earth interiors. And so if this process or related processes, it doesn't have to be as simple as this, to be honest. You know, you can, in certain regimes, you can start crystallizing partially from the top or partially from the bottom and in the middle, so it can be extremely complicated. And if this is operating, then it really changes the dynamics that relative to this simplified picture. And so what we need to do from a theoretical perspective at the moment, I'm a theorist, so you know, this is my perspective, I'm sorry about this, we have to come up with first order predictions that can be tested observationally. At the moment, we don't have these predictions, so I think we're fishing a little bit in the dark at this point. Yeah.
Thank you very much. I just want to add one more thing, but some argue that this could have happened for the Earth. So it could have been a mid-mantle crystallization, and that form the basal magma ocean, and that also predicts some different volatile component, and also the metal composition that could be potentially compared with rock record. So that could be one avenue to make a connection.
Okay, so left.
I'm Kenji Kurosaki from Kobe University. I'm very interested in the interstructure of the post-impact. If the giant impact occurs, then the surface of the crust should be heated. But if the surface of the crust is heated, then upper region of the entropy is high. So in that case, the convection should be stopped due to the entropy gradient. So do you have a comment on the summer evolution after the impact?
Yes, so I agree with you. Actually, we also look into, kind of had a brief discussion in our 2015 paper, but you're right that the outer part of the mantle gets usually shock heated, so that would inhibit convection right after the impact. So as long as the surface has a magma ocean, doesn't have a thick crust, it can cool efficiently. So over time, convection happens at the top and kind of propagates down, and eventually start convecting. But I think there will be some time delay, which I think people haven't really thought too much yet. So I think that's a great point.
Thank you very much.
Okay, so next, please.
John Tobin, NRAO, USA. So on your last slide, you made a maybe rather provocative statement that the accreted composition has nothing to do with the composition of the planet in the end. And while this might be covered a little bit in the talks tomorrow, I was wondering, what is your opinion on the D/H ratio of water on Earth?
All right. Yeah, all right. I need to be careful, of course, what I say in a room full of astronomers now. So, no, I think, of course, it's an overstatement to say that it has nothing to do with it. That is certainly not the case. Of course, planet formation is a very important concept and sets the initial conditions. But, you know, like often case, the prime motivation to understand exoplanets, diversity, and things like this is to understand habitability, whatever this means. And terrestrial planetary environments are very sensitive environments. And so within this context, and this is where we started with the diversity exhibited by the terrestrial planets in the inner solar system, within this context, within approximately the compositional regime of the solar system, the geophysical processes that we discuss in this review indeed completely reset the composition. To give you an example of this, the core of the Earth is underdense by about 10%, and it has been since decades a question, what is actually the component that produces this underdensity? Let's assume it were all hydrogen, like many of Japanese colleagues here have suggested, or a vast majority is hydrogen. Then the amount stored in the core that can also react with oxygen from water is 10 times more water than in the mantle or on the surface. So the vast majority of water on the Earth may actually be stored in the core. So if that were true, then trying to produce scaling laws from theories that deliver water via pebbles or planetesimals are completely dependent on the amount of water that is redistributed between chemical reservoirs. So what we're trying to say is that we need to combine both and extend these processes also in the compositional regime that we see in exoplanetary systems and with the ideas from planet formation theories, but they are not second order things. And we need to combine both the astrophysical side and the geophysical side to get a proper sense of the distribution landscape of compositional scenarios of planets. That's what we are trying to say, I think.
All right, thanks.
Okay, so thank you for waiting. So left, middle, and right. Yes, please.
Yeah, Matthew Bate, University of Exeter. I was just wondering, what about things like Ganymede and Titan? Is the primary difference there just the enormous amount of water? And is the early state of those essentially very hot water worlds?
I'm not sure. Primary difference between the terrestrial planets and the icy moons?
Yeah, exactly. So what does a very young Ganymede look like, for example?
Yeah, if you could, yeah, well, I mean, of course, they have a much larger water content at present day.
Yeah.
Like there are various theories how that comes to be. I think one of the main issues is, of course, that they must form relatively late as well in order to escape much of the heating from initial short-lived radionuclides. I'm not enough of an expert to tell you exactly the current theories on what is specifically about Ganymede. They're most up to date and latest papers. I think the Pearson Nemo paper was mentioned earlier. That was related to Pluto, but it's also relevant for icy bodies like Ganymede, for instance. Do you want to say something about this? No? Okay. Yeah, I think that's the only answer I can come up with on the spot. So sorry about that. Yeah.
Thanks.
All right, Renyu Hu, Jet Propulsion Lab. Nice talk. I want to ask you, follow up on one of the previous questions about TRAPPIST-1 observations and whether these rocky planets would have an atmosphere. So you seem to imply that if the planet has a permanent magma ocean, they are quite likely or should have a volatile-rich atmosphere if the volatile has not been completely stripped away from the planet. Is that what you mean? And would you like to elaborate that or more, like even quantify?
Yeah. I mean, if the planet has volatiles, it has not a sufficient cloud albedo that decreases the net irradiations to values low enough that the planets can escape a runaway process, then the planet will be in a magma ocean state, because the equilibrium point for basically any atmosphere that has a sufficient water content is such that the surface temperature is above the basaltic liquidus, or the basaltic solidus, sorry. And if this is the case, then the majority of volatiles are in the magma ocean, and they are shielded from the strongest effect of atmospheric escape. And that means that yes, as long as the planet has volatiles, there is a redistribution of elements, volatile elements, between the interior and atmosphere base, depending on the redox state at the present state of the planet. And it will be volatile rich, yes. But it doesn't shield it completely from atmospheric escape. Volatiles can escape, like it is discussed in very often in the exoplanet literature. And so until that point, I think there should be volatiles in the atmospheres of magma ocean planets, yes.
Thank you.
Okay, so could be the last question.
Hi, Anish Baburaj, UC San Diego, United States. Is there any way we could determine whether the properties of the magma ocean, whether the freeze out would occur closer to the core or towards the atmosphere?
Yeah, so that depends on the mineralogy. So let's see. So the density difference between the solid and the liquid affects the, so it's like, there are two aspects. One is the relationship between adiabatic temperature profile and also solidus. The way it crosses is where the crystallization happens. Another part is that what's the density difference between the liquid and the solid. So if solid is denser, it sinks, not floats. So we could potentially look into this phase space and relationship between the adiabat and solidus. Although it's not straightforward because we need to understand material properties under high pressure. So I think it's also important to understand the equation of state, Grunitein parameter and such for future experiments.
Can I add just one point? So related to this question, just before actually, there should be a relation between the magma ocean atmospheric composition and interior redox state. And what I mean with interior redox state is just the part that is in equilibrium with the atmosphere at this point. I think this is the quest we have to take. This is exactly the question, right? Is there a non-degenerate relation between interior properties and atmospheres? But we have to have some samples. At the moment, we don't, right? We don't have any atmospheric compositions of super Earth exoplanets, and we need to get those. Yeah.
Thank you.
Okay, so if there are no more questions, let's thank the speakers again. Thank you.